So I just wanted to show you today a good way to think about the Euclidean division algorithm, which is very intuitive and probably maybe it makes sense for you and it clicks in your head, I hope. Well, to start it off, maybe a revision or something which you already know, but just to lay things out, is that what is a GCD? Well, a GCD is a greatest common divisor. So it's a divisor which divides A and B, so it's a common divisor. And it's the greatest one. So if there exists another divisor, so if there exists D prime, another divisor which divides A and B, then that divisor should also divide D because D is the greatest common divisor, right? And that's the definition of common divisor. Well, if you know the prime factorization, well, I think this will really make sense to you, is that you take the most things that are in common. But if you don't know, it doesn't matter. And also one remark is that A and B are not zero, so we take Z without not zero. They shouldn't be zero for our kind of theorems to work. And then some quick simple examples. Let's see 21. If you factorize it, it's 7 times 3 into primes, and then 6 is 3 times 2 into primes, and we see what is in common is 3, so GCD of them is 3. And then we take 27, we see it's third squared and third to the cube and 3 squared, and then we can clearly see that, well, we can take 3 as a common divisor, but it's not the biggest one because we can take 3 squared or 9 as a common divisor. So I just wanted to show you that there are many divisors, but we need to take the biggest one. And the biggest one is those that are as many in common primes as you have. Well, that's not the point for you today. The point is that, well, we can do the prime factorization of things, but the problem is that it's a very hard thing to, in a sense, it's computationally hard, maybe not for us, but computationally it's hard things. So that's how even the encryption things are based, because it's very hard to prime factorize extremely big numbers. And that's the main point today is to derive some algorithm which makes us easy to find the GCD without knowing the prime factorization of those numbers. And that's the Euclidean division algorithm. And then the point is we need a small theorem, I guess, but it's a small idea, is that if you take two integers, let's see 11 or I don't know, 20 and 20 and 7, I guess. Okay, 20 is equal to 2 times 7 plus 6, right? Or you can say 2 divided by 7 is 14 plus a remainder of 6. No, it's 14. I mean, it is 14, but it's 2 and then plus a remainder of 6. And the point is that this kind of way of expressing numbers, if you have this is A and this is B, right? This is A and B, and these two numbers, well, this is called a quotient and this is called the remainder, right? But I like to call this a multiplier and this is a remainder because, I don't know, it feels nicer. And the point is that these two numbers are unique. There only exist for each pair of two numbers, there only exist two unique numbers. So if I take A and B, then these two numbers are unique. That's what the theorem says. We can prove it, but it's not for us today. And then that's what it's saying. There exists an A, B, L, and Z, and then they're not zero. We exclude zeros in this kind of things. There exists a unique pair of a quotient and a remainder, which are also in Z, right? Such that this A is equal to QB plus R. And also, the remainder should be between 0 and B, because if it was greater than B, we could have taken one more B for the remainder. For example, if it was greater than B here, in a sense, we could take one more remainder. Suppose it's this, right? Let's suppose the remainder was all of these, then we could have take one more B from it, right? So it is smaller than remainder, but it's also positive. Also should be positive. It is a theorem, but the idea of it is pretty simple. I took another example, 11 and 5. If you divide 11 with 5, you get a 2, and then the remainder is 1, and these two numbers are unique. And if you express it in a diagram, in a number line, and you express it visually, it's you have A and it goes into B quotient number of time. That's how many this multiplier is. It goes into B, and then because it doesn't go exactly into B, doesn't divide it, the remainder is not 0, then you have some kind of remainder. For example, if you had 10 and 5, then the remainder, there is no remainder. Remainder is 0. You go here 4 times, and the remainder is 0. It just fills up, but many times you get a small remainder, which because it doesn't fit exactly. And then using this kind of like division thing we're doing here, let's try to find the GCD, like the GCD we explained right here, of those two numbers. The main idea of this is, well, here I give a formal proof, but I think first I'm gonna explain it intuitively. What are we doing and what's the point of the things we're doing, and then I'm gonna explain how to prove it formally and so on. Well, I wrote some things in here, but you know what? I'm gonna delete them so I can explain them better, and then maybe it will make more sense. Okay, let's say A in here, or can I just paint A? Oh, nice! I can just paint A. Very nice. And now the first thing is that if you take two numbers, A and B, for example, and you want to find their GCD, well, you know, one of them will be greater. If you take 20 and 10, then 10 is, 20 is bigger than 10, and then you can just assign them randomly however you want. So without loss of generality, how mathematicians like to say it, you can take A greater than B. Because if B is greater, then you can just change the... You can say, what does it really mean? This is easy, but like just to prove it. If you say A is the greatest one and B the smallest one, and then if it was the other way around, when you just can interchange them, right? So it doesn't really matter. This is just a notation. We notate the bigger one with A and the smallest one with B. And then the idea is that, okay, we notice that A is greater than B, and we're asked, okay, well, let's think about GCD. Well, the GCD should divide B, and it should also divide A. Therefore, it cannot be greater than the smallest one. If it is 10 and 20, then the GCD cannot be greater than 10, because it should divide 10, and a bigger number than 10 doesn't really divide 10, so it should be smaller than 10. So we can immediately conclude that the GCD should be smaller than B. Okay, should be smaller than the B number. Okay, now let us check. Let me keep this example in here. Let us check. So GCD is smaller than B, and we want to find the greatest smaller divisor, so why don't we just check the biggest one, right? To make sure it's the greatest common divisor, why don't we just take the greatest B? Why don't we just take the greatest B? Then we can take this B. We can try B, right? The greatest number we can try for the moment is B, so we just try B. So we try B, and let's suppose, well, if you have 20 and 10, if you try B, then you have a 20 in here, right? And then B fits 2 times, so it fits perfectly, which implies that B itself is the greatest common divisor. Now our sense is 10, because 10 divides 10 in here, and 10 fills up 22. Or it divides 20, fills up, and divides the same thing. So if B divides A, then we're just done, it's just B. Because here you would get A Q0 times B with 0 as a remainder, and B would be the GCD. And then the point is, okay, so let's say we have B, let me put some nice colors, but it doesn't divide, so it fits many times. Let's say it fits 2 times in here, or let me make a bit bigger, and then you have a small remainder. Let me take this color, and then you have a small remainder, right? This small remainder. And this is B, this is B, and then you have another small remainder. You have a remainder R0, in our case this is R0. And then, what do we know about the GCD? Okay, we know that GCD should divide A, so let me take a white. So GCD should divide A, so it should fit into A. Well, it should fit into B, right? So this thing should fit perfectly here in a sense. So it should fit into B in here, which implies it should fit in here, which implies it should fit in this whole thing. In a sense, if I draw them, it should fit in here. And we know that it fits this whole quotient times B thing, and we know it will fit this whole A. So it knows it, and then if it fits this whole B, right, and then the quotient starts here and it should end here, it means that it should fit this R0. It implies that our GCD should divide this R0 right here, because it fits this whole A, and then to make this GCD fit in here, then it should also divide R0, which implies that our GCD should also divide R0. And then if it divides R0, then our GCD can be R0 itself, so it can be this big R0, and then we can try does R0 fit this perfectly. Okay, if it does, then pretty good, we found a GCD, but if it doesn't, then we should try a smaller GCD in a sense. So what this division did is that it brought our search space into like a smaller search space. So we now need to find out, we now know that our GCD is smaller than 0. So we know now our GCD is smaller than 0, so what do we try next? Well, logically, if you want to try something next, we try R0. Well, we try R0 and we see if R0 fits in here. But if you want to look like another way to look at it is that we had AB and we take A minus some quotient B, right? And then R0, not really. What I was supposed to do? No. Now we have A minus quotient B, which is just MB itself, and this is R0. In a sense, this is just R0 and B. And now we are checking R0 and B, right? And then we know that the GCD will be smaller than the smallest one in here. And then the smallest one is R0, what we just explained. So now we check the same thing. And now to be sure it's a GCD, we take the biggest option we can take, which is R0, and we check does R0 fit into B. Because if it fit into B, for example, then R0 would fit into B, and R0 fits in R0, right? So if it fit into B, then it would fit in here, and also it fits in here, which implies it would fit at A completely. Okay, but let's suppose it didn't fit. Let's suppose we have some other remainder in here. Let me color it white because too many colors, right? Let's suppose this was the remainder. And this was the remainder. Let's call it R1, right? And well, there are R0s in here. And let's call it R1. And now, okay, in a sense, it's the same thing we had here, and we deduce from this because the GCD fit in here and the GCD was fit in here. We deduce the GCD should fit in here too, because it fits in this part, so it should fit in this part. And we do the same thing. We know the GCD should fit in B, right? And we just prove that it should fit obviously in R0, so it fits in here. It fits in R0, which fits in this part, so it fits in this whole thing. So we know it should fit in here, but if it fits in these two places, then it also should fit in R1. So in a sense, our GCD can be R1, because it should fit in R1, or it can be smaller than R1. So right here, what we did is just made it here smaller than R0, and here we just made it smaller than R1. And what we did is we check again. To be sure it's GCD, we check the biggest one. For our case, it's R1, because we know the GCD is smaller than R1. So we check, does R1 fit in here? And we see, and let's suppose it fits. Let's suppose it did fit. If R1 fits, then we have the smallest common divisor fits in here. R1, it's 2 R1s. Or just, let's suppose it's 1 R1 or 2 R1s or 3, I don't know. Doesn't matter in here. The quotient doesn't matter. Let's suppose it's 2 R1s. When if it fits in here, then it fits in this guy, which fits in the whole thing, and because it's R1 itself, then it fits in this thing. And then if it fits in all this thing, then it fits in B. And we know previously that it fit in R and R, so it fits in here too, which implies it fits in all A, so it divides both A and both B. So this thing, because we always choose the biggest one we could take, then this thing is the GCD. And then a way to write this, well, was you take A and you divide it, right? This is what we did. And then we took B and we divided by R0. And we took our B and we got the remainder R1. And when we took, and we lowered the search space here to R0, to R1. And when we took R0, and when we divided by R1, and then in this case it fit, so plus 0, we didn't get any remainder. And because this thing it fit, then this thing was fit in here, then we could go back and fill all A could be fit by R1 and all B by R1. Well, if you look at it, R0 is made by R1, which means this whole thing, QR0 plus R1, which is this thing, is all made by R1s, which implies B is made by R1, which implies B is made by R1, and then this B plus R0, this implies that B plus R0 is made by R1, which implies the whole A is made by R1. And this is even how the formal proof will work, actually. R1 in here and R2 in here. right? And then till you find Rn. So the idea is that this, like, when you get a 0 as a remainder, this Rn will fill the whole thing, and that will be the GCD, because we always chose like the biggest one that could be GCD. This Rn is equal to the GCD. And also the point is that another point is that, in a sense, what we did is that we had this property that GCD, we started with A, B, and we had this property that GCD cannot be smaller than the smallest one, which we suppose was B. So we removed how much we can remove from A. So we removed A minus how much we can remove Q0 of B, right? And we got the R0 as a remainder. And we know that the remainder would be smaller than B, so we know that now R0 is smaller than B, right? And we know that the GCD should be smaller than these two numbers. They should be smaller than the smallest numbers, which is R0. And then what we did is that, okay, it should be smaller than 0, so let's suppose maybe it is R0, the biggest one we can choose, and we removed it from B. R0, and then here we remove from B minus Q1 R0, and we get R1, and so on until we get no remainders. The remainder is, we get like 0, and we get an Rn here, and this is like Rn is the GCD. So this is what like the really did. So the main idea about it was when we divided A by B, then we got a remainder, and because of a property that the GCD fits in A and it fits in B, when the GCD also fitted in the remainder, and because it fitted in the remainder, that implied that it could be in the remainder or a smaller one than the remainder. But because we always want to find the GCD, the biggest one, we suppose we take the biggest one of them, which is the remainder itself, and then we can just construct like this. And then another thing to say is that it will always end, like we're sure it ends. There is another theorem that we know that it ends, but if you think logically, it's getting smaller and smaller and smaller. So this remainder is getting smaller and smaller and smaller by the division algorithm we had. Like this thing is always smaller than B, right? In a sense, or always smaller than the divides. The remainders are always smaller than the one who divides. And this R1 goes, so R0 is greater than R1, and then it becomes smaller, till we reach something, right? Not necessarily till it's the GCD in a sense. And then this thing will end, and we make sure it ends because, in a sense, if it goes, it doesn't go forever, because 1 will always fit into everything. So we have 1, and 1 will always fit into everything. So we'd go till it reaches 1, right? 1 is a distance, and 1 fits into every integer. So 1 fits into A, and 1 fits into B, 1 fits into everything. So till it reaches 1, which fits into everything, is okay. Yeah, and that was like the logic behind it. And then if you want a formal proof, is you have A and B element Z without 0, and then you do this division, and then the theorem says that this Rn is equal to the GCD, and then to prove it is that we suppose, and then we need to prove a first point in here, the first point that our Rn or our GCD divides A and it divides B. And then to prove that thing, we start with, okay, Rn divides Rn minus 1 here for sure, because it's the smallest one. It's the same thing as we did here, R1 divided R0, right? So Rn divide Rn minus 1, and because it divides, because Rn minus 2 is made out of Rn, which Rn divides, and Rn minus 1, which is divisible by Rn, we can factor out an Rn, for example here, Rn, Qn, and then the remainder of this thing, like what's its remainder after we take out Rn, plus 1. So we can also, and this is the same thing as Rn minus 2, right? This is the same thing I did in here. So here we divide this thing because we can take out an Rn, because this is divisible by Rn, and this is equal to Rn minus 2, which implies we can divide Rn minus 2. And then we can do this, we can go up and up till we reach like this point, and we reach Rn divides this thing, which is equal to B, and then we do the same thing in here, which is divisible by A, and we find that Rn divides A and Rn divides B, so we find that is a common divisor. And then we need to prove that formally, we need to prove that every other divisor, so for all D, that D divides Rn, so Rn is the greatest common divisor. So let's suppose we have a D that divides A, we have a common divisor that divides A, and it divides B. Then this guy, because it divides A and it divides B, then I took this thing in the other side, then it has a common factor you can pull out of A and B, so it divides this guy, it divides A minus Q0 B, which is equal to R0, so it divides R0. And now we know it divides B, and we know it divides R0, so we can pull out the thing, and this is a common factor of that D, and we know it divides R0, so it divides R1. This is equal to R1, and we can go down, 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 down till the end, and we can find that every one we take, every divisor we take should divide R1. Which implies that this R1 is the greatest common divisor from 1, because it divides R1 and RB, and then for every other divisor we have of a common divisor, it will divide Rn, so it is the greatest common divisor. So Rn is the greatest common divisor. And then and this is how you prove. And then you also have to prove that it ends, the sequence ends, and then there is like formally there is like a in sense that in the whole numbers there exists the smallest element if you take some of them. So there, and then because this also gets smaller and smaller, it will end because there exists the smallest element. And generally, this is what I wanted to say. I just wanted to explain like this idea. Because this is good, right? You can understand this in a sense formally, but what it's really saying is that you have Rn, and you find at the end, and this Rn divides this guy, and then this, and then it divides this guy, and also it's itself in here. So it should divide this whole thing, which itself is this thing in here, and then it divides this whole thing, but because it divided this, and it divides this too, and then it divides this whole thing. And that was the point of it. And the second point was that when we divide it by this thing, we find the remainder, and the remainder kind of said to us that it should be, because GCD divided this and this, then it filled up this, right? So with smaller things. Now maybe it makes more sense. It filled up the smaller things, same in here. Right, and then it filled out the smaller thing because it should be divide A, which implies that if it divides till here, then it should fill up exactly this thing. So that's what we like kind of deduce that it should be R0, or it should be less than R0, and to make sure it's always the GCD, we got like the biggest one we could take for the moment, which was R0. And so on, we just like lower down the search space until we reached the GCD. And that's like, oh, did I take? Yeah, we can also like take a simple example. Let's actually take two examples. Let's take 12 and 4, right? And then we will take also 7 and 3. Because 7, I want to take 7 and 3, they are primes, so the GCD is just 1, they're co-prime, we say it. And we will see like we can get till the end, it's 1, and 1 will fill up everything. So let's take an example. We have so let's take a GCD of, I won't try GCD, I'll just write like, what I say, 12 and 4? Yeah, it's 12 and 4. Well, I know I think it's 2, right? Because it's 2 times 2. Well, if you look at the prime factorizations, it's 2 squared, and then 2 times 3. No, this is 4 times 3. This is gonna be 4, right? Let me take 6. Yeah, 6 is 2. No, it's actually 2 and 3, so it is actually 6. Let me take 8. Let's see, 8 is 4. Okay, 12 and 8 is gonna be 4. Right? This is gonna be 2 to the third, this is gonna be 2 to the second times 3, so it's gonna be a 4. Now, the way we do it is like I draw 12, right? I would, maybe it's a bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Okay, 0, 1, 2, 3, 4. Or I can just omit this step. You understand it, I think. I'll just write 0 to 12, and then I'll suppose it's 8, and then 4 are left, right? So, and now we have a 0 to 8, and then 4 are left, this is 12, and then 4 are left in here. So this is the remainder 4. And this is B, which is 8, and there is only one B. It's the remainder R0, this is A, and since what we did is R0 is 1 times 8, 12 is 1 times 8 plus 4. Right? Yep, nice. And then what we ask is how many times does R0 go into B? Well, well, we know that GCD is gonna be less than or equal to 4, right? And what we do is that R0 goes 2 times. This R0, R0. And then what we know is that we can do it here too, is equal to 2 times 4, and which implies that 4 is the GCD, so GCD is 4. And we like writing like this, 4, 4, and it implies like we know that this thing will fit in B, and this thing will also fit in A, and then will also fit in R0, so it should fit this whole A. So it should divide both A and B, and it is the greatest one because we know when we divided A by B, then this thing fits in here, and our GCD should fit B, should fit this thing, and also this thing, so it should fit R0. And then we thought is greater than or equal to 4, and we took 4. That's the main idea behind it. And we take 7 and 3, these are like coprimes. Then it's very interesting because we need to get the 1 in a sense because they have nothing in common when you look at the prime factorization. We get a 0 to 7, and then we get 2 3s, and we get the 1 as left over. So R0, we get B, B, A, we get 1, 1, and then we get 3, 3, which is 6. And this is the same thing as saying here 7 is equal to 2 times 3 plus 1. And then we have 3 is equal to 3 1s in a sense, 1 times 3 times 1. So 1 is their GCD because 1 fits. Well, 1 is GCD of everything is a common divisor of everything, right? Because it's that the unit in a sense, it fits. So this is like R0, 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 which is 1, 1, 1. This fits in here, and this is also fits in here and here. So it fits in this whole thing and this thing, which is just A. And you can like go, and you can like, if you get bigger numbers, you're gonna have to go like deeper and deeper and deeper until you find your GCD. Yeah, and that's all for today. Thanks for watching, and I hope like you got a deeper understanding how like you would come up with this algorithm, and see you